This is SpaceTime Series 27, Episode 37, for broadcast on the 25th of March, 2024. Coming up on SpaceTime, a new spin on the red supergiant star Betelgeuse, how asteroid and comet bombardment changed the moon forever, and New Zealand's Electron rocket undertakes its first NRO launch from American soil. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A new study suggests that evidence of what appears to be a faster than expected rotation observed on the red supergiant star Betelgeuse could instead be its violently boiling surface. The high spin rate was detected a few years ago when astronomers began focusing on Betelgeuse after it began to dramatically change in brightness. The behemoth rapidly dimmed from being the ninth brightest star in the night sky down to below 20. The star's dimming in brightness led to speculation that it was about to go supernova, which is the next logical step in its evolution. Betelgeuse is expected to explode as a core collapse or Type 2 supernova pretty well any day now, which in astronomical terms could mean 1 million years from now, or it could mean tomorrow. When it does explode, Betelgeuse will temporarily outshine all the other stars in our galaxy, and it will be clearly visible in the daytime sky here on Earth. The last star seen by humans to go supernova in our galaxy was Tycho's star back in 1572. That was before the invention of the telescope. However, the dimming of Betelgeuse was later put down to the expulsion of a massive cloud of dust which blocked our view of the star. Located somewhere between 530 and 643 light-years away, Betelgeuse is the brightest star in the constellation Orion, and one of the largest and most luminous stars visible with the unaided eye. The red supergiant represents the scorpion's sting on Orion's shoulder. Now, although I've been calling it Betelgeuse, it's more commonly these days referred to simply as Betelgeuse. Don't say the name 3 times. But the name has gone through centuries of tortured mispronunciation. It originally started out as Betelgeuse, meaning the hand of the big man in Arabic, the big man being Orion the hunter. Betelgeuse began its life only about 10 million years ago as a massive spectral type OB blue star. By comparison, our much smaller sun is some 4.6 billion years old and will probably keep shining for another 7 billion years. That's because the sun's much smaller than Betelgeuse and so burns through its nuclear fuel supply much slower. Calculations of Betelgeuse's mass range from slightly under 10 to a little over 20 times that of our sun, with some 100,000 times the sun's brightness and around 1,100 times its diameter. If Betelgeuse were put where the sun is at the center of our solar system, its surface would extend out to almost as far as Jupiter, therefore engulfing the orbits of Mercury, Venus, Earth, Mars, and the main asteroid belt. But Betelgeuse's future is limited. It is now a bloated, old, semi-regular variable red supergiant. Red supergiants are the largest stars in the universe in terms of their volume, although they're not the most massive or luminous stars around. Now, stars this big aren't supposed to rotate very fast. In their evolution, most stars expand and spin down to conserve angular momentum. However, recent observations suggest that Betelgeuse is rotating incredibly fast at some 5 kilometers per second, and that's 2 orders of magnitude faster than what a single evolved star should be spinning at. The most prominent evidence of Betelgeuse's rotation has come from ALMA, the Atacama Large Millimeter Submillimeter Array Radio Telescope in Chile. ALMA's 66 antennas work together as a giant single dish, a technique known as radio interferometry. Using this technique, astronomers discovered a dipolar radial velocity map on the outer layer of Betelgeuse. Now, put simply, the data shows that one half of the star appears to be moving towards us, while the other half, the opposite half, appears to be rotating away. That tells scientists the star is spinning, and the rate at which that occurs tells us exactly how fast the star is spinning, and Betelgeuse is spinning quickly. Now, this interpretation should have been a clear open and shut case. That's if Betelgeuse was a perfectly round sphere. However, the surface of Betelgeuse is actually boiling quite violently. The heaving and convecting bubbles can be as large as the Earth's orbit around the Sun, which means it's covering a significant fraction of Betelgeuse's surface. And these convecting bubbles are rising and falling at speeds of up to 30 kilometers per second. Now, based on this picture, an international team led by Jingzi Ma from the Max Planck Institute of Astrophysics in Germany has offered an alternative explanation of Betelgeuse's velocity map. What we're in fact seeing is Betelgeuse's boiling surface mimicking rotation. Reporting in the astrophysical journal Letters, Jingzi Ma proposes that a cluster of boiling bubbles rise on one side of the star, while at the same time another group of bubbles is sinking on the other. Now, due to the limited resolution of the Alma telescope, these convective motions would be blurred in actual observations, and that could result in the dipolar velocity map. The authors developed a new post-processing package to produce synthetic ALMA images and submillimeter spectra from their three-dimensional rotational hydrodynamic simulations of non-rotating red supergiant stars. They found that in 90% of simulations, the star would be interpreted as rotating at several kilometers per second simply because of the large-scale boiling motions on its surface. And those motions couldn't be clearly identified in the ALMA telescope. Of course, further observations are now needed to better assess the rapid rotation or surface boiling of Betelgeuse, and the authors are hoping to make predictions for future observations with higher spatial resolution. Fortunately, other astronomers have already made higher resolution observations of Betelgeuse in 2022, and that new data, which is now being examined, will test this new hypothesis. We'll keep you informed. This is SpaceTime. Still to come, how asteroid and comet bombardments have changed the face of the moon forever, and New Zealand's Electron rocket has undertaken its first NRO launch from United States soil. All that and more coming up on SpaceTime. A new study has found that the Earth's moon may have been subjected to far more asteroid, comet, and meteor impact events than previously thought. The findings, reported in the journal Nature Communications, provides a new picture of the moon's earliest geological evolution. The study's lead author, Katarina Miljkovic from Curtin University, says the new research is providing greater insight into how the oldest impact events on the moon may have left near-invisible cratering imprints, offering a unique perspective about the evolution of the Earth-Moon system. She says the lunar craters may have looked significantly different if they occurred while the moon was still cooling following its initial formation. If these large impact craters, often referred to as impact basins, formed during the lunar magma ocean solidification period, that's more than 4 billion years ago, they should have produced different-looking craters compared to those that formed later in the moon's geologic history. A very young moon had formed with a global magma ocean that cooled over millions of years to form the moon we see today. So, when asteroids and other bodies hit the softer lunar surface, it really shouldn't have left such severe imprints. In other words, there would have been little geological geophysical evidence that the impacts had occurred. Miljkovic says the time frame for the solidification of the lunar magma ocean varies significantly between different studies, but it could have been prolonged enough to experience some of the large impact bombardment history typical of the earliest periods of the solar system's evolution. As the moon ages and its surface cools, it becomes harder, and the bombardment imprints are a lot more noticeable by remote sensing. Miljkovic says it's imperative to understand the bombardment and cratering record of the earliest epoch of the solar system's history in order to complete the story of how the sun's planets formed and evolved. Right now, the moon's thought to have formed through a collision between the early proto-Earth and a Mars-sized planet called Theia, which slammed into the Earth. That caused both bodies to melt, forming a magma ocean, eventually solidifying to form the Earth. But some of the ejecta from that collision was flung into orbit around the molten body. That eventually coalesced and formed the moon. That was 4.5 billion years ago. But it wasn't the end of impact events. As Jupiter moved in towards the inner solar system and then back out again to its current orbital position, it flung a lot of small objects all over the solar system, creating what astronomers call the Late Heavy Bombardment. That was about 3.9 billion years ago. And we think that's where the Moon got most of its craters. But of course, it's all hypothesis. By comparing different perspectives of asteroid dynamics and lunar evolution modelling, research suggests that the Moon may have been missing evidence of its earliest cratering record. Michkovitz says her research aims to explain the discrepancy between theory and observations of the lunar cratering record. Translating this finding will help future research understand the impact that the early Earth could have experienced and how that would have affected our planet's evolution.
Well, we've been looking at big craters on the Moon for a number of years. And then what actually allowed us and enabled us to actually start looking into these big craters in more detail was the NASA Grail mission that orbited the Moon. Several years ago, we had a really beautiful mission that mapped the gravity of the Moon in a very high resolution. And that new map gave us insights into the subsurface structure and the crustal structure of the Moon. And because impact and big craters really make an imprint in the crust, and we can start looking at those big craters with a different set of eyes, if you will. So that's kind of the origins of starting to look in those big impacts on the Moon and lunar bombardment in the first place.
You got some really great results from Grail, which gave you some fascinating insights.
So the Grail gave us a new resolution, like an updated, a better resolution observation of the subsurface. What we get is with the gravity signature, as the spacecraft were flying around and orbiting the Moon, they were actually mapping the gravity field, and with that, the distribution of mass and different densities in the subsurface. Because obviously, as gravity varies, it varies because mass distribution is different and the density is different in the subsurface. So we could look at, when we subtract the topography, we could actually look at these different mass concentrations in the subsurface of the Moon. So we started looking more at what's happening in the crust, what's happening in the upper mantle, and with that, an impact. That was my particular interest, was to look at how these big impacts form. So one of the things that we noticed very early on is that if we look at all the Mare region, those are those big impacts on the Moon. So you look up on the Moon and you see all the dark areas, the Mare regions, they're actually floors of these big craters. So when we looked at the eyes of gravity and reverted that in crustal thickness map, we saw that the crust is quite thin at the bottom of these craters across this Mare region. So I started doing some numerical modeling of how these big impacts would form, and it turned out that because the crust is quite thin on the Moon, like 34 to 43 kilometers in thickness on average, what we turn out for those big craters that are 1,000 kilometers across, when impact happens, they actually not only excavate the crust, they excavate the mantle as well, and they pull mantle closer to the surface. So as a product of crater formation, we actually end up with the crust in the bottom of these craters to be quite thin. So that was one of the big things that we could survey and explain the structure of the crust and the crustal thickness distribution on the Moon and connect it to the crater formation. And they say, predict that, thinning comes from impact craters. We can then look at different thermal evolution models and understand how Moon actually evolved as a Moon. So that was all back a while ago, just after Grail have given us the first data. But one of the outstanding things that was bothering me for quite a long time was actually to understand the very early evolution of the Moon. And that's the new study that just came out. What got me interested is thinking about this massive bombardment, and because we know that there have been
now, when you say massive bombardment, are you talking about the late heavy bombardment about 3.9 billion years ago?
Yes, I'm thinking about late heavy bombardment, but the thing is the term late heavy bombardment is becoming obsolete a little bit, because the late heavy bombardment has been is a term that describes the earliest formation of the solar system after the planetesimals have formed and the planets have just formed as young planets, and there has still been some leftover bombardment coming from asteroid belt or just the disturbances around the inner solar system. And because we have the record on the Moon that kind of seizes at 3.9 or 3.7 even billion years ago. We don't really know. We have a tail of this late heavy bombardment, but we don't have the beginning. We don't know how the beginning of the late heavy bombardment looks like, which is why the term of late heavy bombardment, because we don't have the early heavy bombardment. We don't know how that part of the impact bombardment looks like.
All that's important because that lets us know when Jupiter did its grand tack.
Exactly. Yes, it's important because it tells us about this kind of final stage of planet formation. So it really gives the initial conditions to all the planets that we see in the inner solar system, including why all in the planets different and why all different sizes and why they all seem to have a different habitable or inhabitable conditions and so forth. So definitely we do want to know what are the initial conditions, if you will, for the formation of the solar system. So that's why we really all try to understand the earliest bombardment as best we can. When we look at the moon, we can determine something a little bit about this late heavy bombardment, or some people call it terminal cataclysm, but we don't know what happened before then, whether we had even a higher flux or whether we had a lower flux, but then there was the disturbance that agitated asteroid belt, like you were saying about Jupiter passing, and that caused the excess bombardment around that period. So we don't really know that. And I think a lot of the new studies have been coming out trying to explain kind of the front end, or if you will, of that heavy bombardment period. So my study is trying to give some insights into that, because when we look through the Grail data, we see that there is different. I mean, it's not only through Grail data, to be perfectly fair. There's been other studies in the past looking at lunar basins and these big craters. Some of them look like more relaxed in geologic morphology or geophysical signature than others. So I started thinking about the notion of like, well, what if we had bombardment before the late heavy bombardment? That was also heavy, but it happened on the moon while moon was still cooling. So we know that the ongoing or the
during
leading
its
theory
scummy state.
Yeah, and it's a gummy square. Call it a squishy moon, if you will. Some wanted me to call it cheese, but cheese is not as squishy when you hit it. It's mostly like that kind of a squishy state. So the thing is, so we know that the leading theory for the lunar formation is that an impact of the size of Mars hit the early Earth and broke off a little bit of material from the Earth, and those two have actually collided into kind of a new disk, and that disk seeded our moon. That's an ongoing theory for the moon formation. So if you had this young moon forming, because it's coming from this kind of spun out little disk and around the Earth, it has to be hot. It has to form kind of a little magma ball. So we don't really know how long it took for that magma to cool and solidify and form the moon as we know it today. But we know that, well, what we think we know is that it had a magma ocean that was global, and it started to cool. Whether it cooled within 10 million years or 500 million years, which would be kind of like the longest ever, we don't know that. Some theories suggest very short period of solidification, which are mostly like petrographic, petrological, or petrochemical calculations. But if you add any kind of dynamic instability, like tidal effects or more impacts or anything dynamic, that cooling period has to become longer, because you're not just cooling a system, you're adding more complexity to it. The point is that there is, let's say in the last 10 years, there have been studies that showing that if there is any kind of instabilities going on in terms of moon's orbit around the Earth and any kind of tidal motion and different things, that cooling of the magma ocean can last maybe a couple of 100 million years. And all of a sudden, it's kind of biting into this bombardment period when you say, hang on a minute, but surely if that is that long, then surely there should have been some impacts happening in that period as well. So kind of that's where the idea for this modeling work came to be. So I've done series of simulations that would kind of mimic bombardment under the residues of magma ocean, if you will. So if there was partly solidified mantle, there is a flotation crust on it and kind of sandwich layer of melt between the crust and the mantle, then we're kind of modeling late stages of solidification of the moon. And all the impacts that the simulation of these big impacts that I ran, it's showing that because of that little sandwich layer of melt, that the crust ends up being squishy, if you will. So it basically relaxes and comes back to almost the original structure as if like before impact. So if we were to look through the eyes of gravity, looking for those subsurface differences in mass, we might not be able to see them because the crust and the mantle just relaxed back to the original position, almost the original position. So when we look at them today, we just simply can't find them. And I think the smoking gun in this whole story wasn't just the fact that the crust in the mantle relaxed and you don't see it in gravity, but that if you look at the moon or all the kind of ongoing stuff that we know from observations, is that there are these so-called multi-ring basins on the moon. So it kind of has a rim, but there are some rings around it, like Orion or other big basins that preserve the topographic structure. What the modeling showed is that if the moon has been, let's call it squishy, that we can't have those spaced out rings forming. Instead, what we get is kind of a graben structure with multiple rings kind of happening very close to each other. So if you look at Jupiter's moons, like Ganymede, for example, or even Europa, but Europa has a lot of tectonics going on. But those icy moons, they actually have this kind of palimpsest basins. They have this kind of circular but graben structure rather than ring structure. And I actually was getting more of that kind of morphology happening on the moon while there was magma ocean than the regular ring structure that we see on a cooled moon. So that kind of also was, I think, the smoking gun showing that not only that you can't see it in subsurface structure, you also can't see it on topographic structure.
Yeah, but on Ganymede, that graben structure, that could be because there's a subsurface ocean there.
Potentially, yes. So some kind of a different rheology happening in subsurface. Yes. Exactly. Definitely. It's all to do with the kind of the strength of the lithosphere and the response of the kind of body and how rigid it is when an impact happens.
Are you seeing lots of differences between the structure of craters on the near side and the far side of the moon? We know they two look very different. This dichotomy of the lunar surface is very famous, but it's always been put down at differences in the thickness of the crust. Are you seeing that in the craters themselves?
Yes, we do, and we had a study in 2013 that came out of direct Grail analysis that showed that when we really compare the size of near side basins with the average size of big basins on the far side, that we see that the near side basins are actually much, much larger, so almost twice as big than on the far side. So the argument was, if we assume that the lunar surface were to be bombarded equally across all sides, so there is no preferential direction between near side and south side, and the asteroid dynamics really doesn't support any preferential direction, then we would assume to have kind of a randomized distribution of impact on both hemispheres, but we don't. We see 8 big craters on the near side, and then only one of that size, or the size category on the south side. And that one is also kind of on the limb, close to the near side. So the explanation to that kind of funky statistic comes from interior. So it comes from asymmetric thermal evolution of the moon. So at the time when these big basins have formed, so we're now talking more about late heavy bombardment, if you will, or thermal cataclysm. So the big impacts that have occurred, and the moon had cooled enough so it can capture and preserve them in the record, in a cratering record. So what we're seeing is that if the near side had a hotter subsurface, so kind of a higher temperature gradient, so it had a hotter subsurface because of high concentration of radioactive elements that we call this the so-called creep terrain on the near side, that would have caused the localized increase in temperature in subsurface compared to the far side that started cooling down normally and had a cooler thermal gradient in subsurface. So when we do simulations on a hot target versus cold target, we actually end up, for the same impact conditions, near side basins could be up to twice as large as the ones on the far side.
Is that due to tidal locking?
You mean the temperature asymmetry or the impact?
Temperature asymmetry.
That still remains an open question. I think the simplest explanation would be that it has to do something with the tidal locking, with the tidal forces that causes the near side hemisphere to A, have a thinner crust, and B, also somehow has those heat-producing elements,
different minerals,
kind of like concentrated under the crust on the near side. We don't have an explanation yet, like a smoking gun theory that would say what promoted the asymmetry. Some people even suggested there could have been an impact, but that theory never really held water. So I do believe that if I were to believe in a simplest solution, Occam's razor, I would probably say it probably has something to do with the gravity and the fact that the young moon had formed quite closer to the Earth compared to today, because moon had been moving away from the Earth as beyond
the fingernails.
Time is passing. It goes away at the rate of how our fingernails grow. The earliest impact that happened on the moon at 4.5, 4.4, maybe 4.3 billion years ago. Probably in the first, let's say, 100 million years.
Yeah.
We don't even have that in the geologic record of the moon. We can't peg any absolute value, absolute age to any of the basins to be that old. And it's simply because I think when they form really already relaxed, so it's hard to find them. But it's also hard to find them because they're the oldest. So there has been overprinting of new impacts on top of it. And, so I think that if I were to look for them, I'd just say I'm not. Whoever wants to try look for them, good luck. I don't think they'll find them. But the whole point of the study wasn't to go look for them, is to bridge the gap between different discipline research, if you will. So if we look at astrodynamics, they've came up with the late heavy bombardment and the NIS model and to explain the observations. But if I say, well, you don't need to bother explaining the observations because impacts have been happening throughout the entire early history of the solar system or the moon, if you will. So you don't need to explain the blip in observations for the late heavy bombardment. It had been, let's say, if we assume it's been a steadily declining impact flux since 4.5 billion years, to present day, there haven't been much of a disturbance at all, and you don't see it in observations. Well, here is an explanation why you don't see it in observations, because they're invisible. It's very hard to come up with a scientific theory that claims something's invisible, but I've provided a whole lot of justification as to why we wouldn't see it in the record, which gives then the input to all the numerical modelers looking at astrodynamics that they don't need to satisfy observations as we see them, because they could have been the early period that won't leave an imprint.
The early stuff hasn't left an imprint, so that's why there appears to be a late heavy bombardment period, but there may have been just as much stuff earlier on, just that would not have left an imprint.
Correct. And I'm not saying that the late heavy bombardment didn't happen. It could have been of a less of an intensity. It could have been with a different abnormality. It could have still been an event that Jupiter brought in as a disturbance into the inner solar system. But what I'm saying is that the solar system before that point in time may not need to be quiet, if you will. It could have still had events and bombardment and and impact flux going around the inner solar system. I think probably the key thing would be to try and look for those evidences in other planetary bodies as well in the inner solar system. So if we can find it elsewhere that could be evidence of this earliest bombardment moment, then it could tell us something more about and confirm the theories we have about the moon as well.
That's Katerina Miličković from Curtin University. And this is SpaceTime. Still to come, New Zealand's Electron rocket undertakes its first NRO launch from American soil. And later in the science report, the World Meteorological Organization confirms that climate change has smashed all records for greenhouse gas levels, temperature, and sea level rise. All that and more coming up on SpaceTime. Rocket Lab have finally undertaken their first Electron mission for the United States National Reconnaissance Office from their new launch complex at NASA's Wallops Island Flight Facility on the Virginian mid-Atlantic coast. The launch, named Live and Let Fly, was the 46th mission for the Electron rocket. The highly secretive NROL-123 mission carried 3 classified payloads into orbit. All previous Electron launches for the National Reconnaissance Office have taken place from one of Rocket Lab's 2 launch complexes at its Mahia Peninsula Launch Complex on New Zealand's North Island. This is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with the Science Report. A new study by the World Meteorological Organization shows that climate change has smashed all previous records for greenhouse gas levels, surface temperatures, ocean heat and acidification, sea level rise, Antarctic sea ice coverage, and glacial retreating. Additionally, they found that increases in heat waves, floods, droughts, fires, and cyclones have cost the global economy billions of dollars. The World Meteorological Organization study says that 2023 was on average 1.45 degrees centigrade above pre-industrial baseline levels. Glaciers suffered the largest loss of ice on record, and the Antarctic sea ice was 1 million square kilometres below the previous record year. However, they do say there was one small glimmer of hope in the data. Renewable energy generation has increased by almost 50% over the previous year. A new study has found that getting the recommended 7 to 9 hours sleep a night is currently well out of reach for almost a third of people. The findings, reported in the journal Sleep Health, found 31% of adults had an average sleep duration outside the recommended range. The research by Flinders University found that only 15% of people slept the recommended 7 to 9 hours for 5 or more nights per week. And among those who did achieve the average of 7 to 9 hours per night over the 9-month monitoring period, about 40% of the nights still fell outside the ideal range. Assessments of 86 United States government staff and family members who developed mysterious symptoms after serving overseas, something which has become known as Havana Syndrome, have failed to find any significant clinical differences between these people and a group of unaffected people. Sufferers have reported intrusive sounds and head pressures, often alongside dizziness, pain and visual problems, among other symptoms, after serving overseas. A report in the Journal of the American Medical Association says 2 new studies have failed to find any significant differences in brain structure or in most tests of auditory, vestibular, cognitive, visual function or blood biomarkers between the 2 groups. In fact, the only differences they could find were in self-reported and objective measurements of imbalance and symptoms of fatigue, post-traumatic stress, and depression. A new study claims a growing number of women are turning towards non-traditional spiritual beliefs. These include witchcraft, the occult, crystal meditations, as well as tarot card and psychic readings. Tim Mendham from Australian Skeptics says the IBIS industry report claims numbers have been increasing for years now, with the COVID-19 lockdowns providing an added additional boost.
Yeah, for a start, when I first read that headline, I was surprised. I didn't know they were turned to witchcraft, but this story actually covers a whole range of different alternative practices like tarot reading and psychics and crystal ball gazing and everything. It's not really witchcraft as you think of it. And they're trying to think, are women turning to such practices of late? And why it might be happening. Now, you have to be very careful about these things. You obviously got very great danger of gender stereotyping and that sort of stuff. But as a background, in America, the psychic industry has grown by about 2% a year. The number of psychic crystal tarot card businesses has grown by 1.6, and it's worth about $2.5 billion. I think I reckon it's a lot more than that, actually, these days. So it's a decent-sized industry that's making a lot of money. That doesn't necessarily explain why people might be turning to these things. And the question is, are they turning to them? Well, the suggestion is that women are more inclined to believe these things than men. One survey showed that women are more likely to say they felt the presence of a ghost or a spiritual entity, about 46% of women, compared with men, about 30%. A similar trend can be seen also in the belief in psychics, where 40% of women versus 29% of men. So the question is, why are women more inclined to believe in these sort of things than men? Could it be that men are more grounded in physical, tangible things and women are more spiritual?
Yeah, men sort of go for the UFOs and Bigfoots, don't they?
By and large, they do, yes. In these sort of things, which are the more spiritual things, you tend to get a high proportion of women, and they're all equally unsupported scientifically, the things that they believe in. It's just a different set of tools, you might say. And the tool is for the reason they're suggesting that it's always the reason put out is that in uncertain times, people are searching for certainty. People don't like the idea that fate is tough, right? Anything can happen to you, accidents do happen, coincidences do happen, and that there is no rhyme or reason to necessarily what's happening to the world or to
Fate
you.
Fate doesn't care.
Fate doesn't care at all, and people want to be cared about, so they're turning to something which gives them a pole to hang on to during the flood. There is something that they can sort of think, this is real, this is something that I can get some emotional support from in a world that looks like it's just totally random. That's a theory which is put out there quite often. Whether women are more aware or concerned or scared of a world which is uncertain. Perhaps that is the case, and therefore that might account for why there's a stronger belief in some of these spiritual beliefs as opposed to the monster beliefs and that sort of stuff. Yeah, the trouble is you get all sorts of suggestions as to why it might be happening. You get all sorts of people who are hopping on a bandwagon. Obviously, the psychic fraternity would be saying people are seeing more in their lives and opening up to opportunities. The psychologists might say it's filling a gap in their lives. So there's various suggestions. It has always been the case that women have believed more in these sorts of things, these spiritual things, than men have. People have often wondered why, and I think we'll be going on for a while trying to sort of figure this one out.
That's Tim Mendham from Australian Skeptics. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favorite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more space time, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.